Linear regression started in the late 1800s, introduced by a scientist named Sir Francis Galton, who was related to Charles Darwin. Galton was curious about the connection between parents and children's heights. He wanted to determine how traits like height are passed down in families. To do this, he came up with a way to draw a line that best fit the data, and he called this idea regression to the mean. This method became the basis for what we now call linear regression. Linear regression became important in statistics, and later in machine learning, is a way computers learn from data. Another scientist named Carl Pearson helped improve Galton's idea and created the correlation coefficient, which measures how strong the connection between two things is. Linear regression isn't just about predicting numbers. It helps us understand how different things are related, making it useful in science and math. Whether it's predicting house prices or trends in the stock market, linear regression is a go-to tool because it's easy to use and interpret. It's a great example of how sometimes the simplest tools can be the most powerful. Let's imagine you have data about the prices of mobile phones based on their screen size. On the left, we have a table showing 5 data points. Each row represents a screen size in inches and its corresponding price in dollars. On the right, we have a scatter plot that visualizes this data. The x-axis represents the screen size and the y-axis represents the price. This kind of data is perfect for creating a model, such as a linear regression model, which can predict the price of a screen based on its size. You want to use this data to predict the price of a new phone with a different screen size. We'll walk through this step by step using linear regression to fine-tune our predictions. Before we start making predictions, let's talk about the approach we'll use and the formula behind linear regression. Our goal is to find a straight line that best fits the data, and this line will help us predict the price of a mobile phone based on its screen size. The formula for this line is price equals m times screen size plus b, where m is the slope of the line, which tells us how much the price changes for each increase in screen size. The b is the intercept, which is the price when the screen size is 0. Even though that's not realistic here, it's part of how the line is calculated. Our job is to figure out the right values for m and b to make the line fit the data as closely as possible. We'll start with an initial guess, and then adjust the line step by step until it's as accurate as we can make it. Let's begin by guessing a line. We'll randomly choose a slope and intercept. Let us start with slope equals 20 and intercept equals 200. So price equals 20 times screen size plus 200. Next, we calculate the predicted prices using this line. As expected, the predicted prices are far from the actual prices, meaning the errors are large. Now calculate the error for each point. This is the difference between the predicted price and the actual price. At this stage, the total mean squared error, MSE, is quite high, around 8100. This shows that our line doesn't fit the data well, so we need to adjust it. Mean squared error, MSE, is computed by first finding the difference between each predicted value and the actual value. Then, you square each of these differences to make them positive. Finally, you average all the squared differences to get the MSE. This gives a measure of how far off your predictions are on average. Now, let's make our first adjustment. We'll increase the slope to 50 and change the intercept to 50. Then compute the price using the new equation, 50 times screen size plus 50. Now, let's calculate the errors again and see if we're getting any better. Look at that. The errors are getting smaller. Our mean squared error is now 1,875, much lower than our initial guess of 8,100. But we can still do better. Let's make another adjustment. This time we'll fine-tune using slope as 60 and intercept as 20. Then compute the price using the new equation, 60 times screen size plus 20. The predicted prices are getting close to the actual prices. Now, the mean squared error is down to 900, which is a big improvement from our earlier attempts. Let's make another adjustment. This time we'll fine-tune the slope and intercept using slope as 70 and intercept as 0. Then compute the price using the new equation, 70 times screen size plus 0. The predicted prices are getting higher than the actual prices. Now, the mean squared error has increased to 3475. In the 4 attempts we made, the best line that fits our data is with slope 60 and intercept 20. This formula is our linear regression model, and it allows us to make predictions for new phones that weren't part of our original data. By using this model, we can easily predict the price of a phone based on its screen size. For example, if we have a phone with a 6.2-inch screen, we just plug that value into our model like this. 60 times 6.2 plus 20, giving us a predicted price of $392. Linear regression works by finding the best fit line to predict prices based on screen size. The goal is to minimize the mean squared error, MSE, by adjusting the slope and intercept. As we repeatedly tweak the line, we reduce the error, improving the model's accuracy. Once trained, this model can reliably predict the price of any new phone based on its screen size. This is how machine learning models learn from data and become powerful tools for solving real-world problems. Thank you for watching this video.